Thank you. Hello, everyone. My name is Yuhong. I'm from Columbia University. Today, I'm going to talk about Octopus, enhancing CXL memory pod via sparse topology. This is a collaboration with my co-author from Microsoft, University of Washington, and University of Wisconsin-Madison. So to give a quick overview, memory is expensive, accounting for half of the server capex, but is heavily underutilized due to stranding. CXL enable a pod of server to reach a common memory pool, enable multiplexing memory demand across server. Besides pooling, CXL also enable intra-pod communication at memory-like latency. However, existing CXL pods are either expensive when using CXL switches or are small when using multi-port device, usually with low port count. To solve this problem, we built Octopus, a low-cost, large-scale CXL pod which sparsely connects server with low-port CXL device without relying on expensive switches. To balance the conflicting demand of memory pooling and intra-pod communication, Octopus partitioned a pod into island. Evaluation shows that Octopus delivers 16% memory saving and with less than 1 microsecond for intra-pod communication. So in 2023, memory is already accounting for half of the server capex in data centers. And the recent memory demand surge from building AI data center make memory even more expensive, increasing the DRAM price by more than 10x in half a year. This plot shows how the DRAM chip price changed within a year. So before the spike, memory is already expensive, accounting for half of the server capex. And now it's even more expensive. Given that memory capacity is going to be expensive and limited in the near future, improving the utilization of memory becomes critical. So a key cause of the low memory utilization is because for data center operator, they need to provision memory capacity based on the per server peak demand. However, the memory use is usually highly uneven across different servers. There are servers where they run out of memory, while other servers have idle memory that are being wasted. And the idle memory capacity cannot be used by other servers, causing them to be stranded. A promising solution to this problem is to use Compute Express Link, or CXL, which enable memory pooling across multiple servers. So instead of provisioning a fixed amount of memory for each individual host, as shown in this plot, CXL allows server to connect a pool of memory through the CXL link. So by pooling memory, CXL can multiplex the memory demand across different servers. CXL memory can be allocated to each server in an on-demand fashion, which means less stranded capacity. And when provisioning memory capacity, we can provision for the aggregate peak, not the per server peak. We term the set of servers that connect to the same memory pool as a CXL pod. So you might ask, how much memory can we actually save by doing pooling? The answer is that depends on the number of servers within a CXL pod. So this plot from a recent work shows how the saving from memory pooling changed with the pod size. So as we can see, effective memory pooling requires a few dozen of servers, which allow data center operator to provision about 20% less memory capacity, which is a huge capex saving. Besides memory pooling, CXL has another important use case to enable the server-to-server communication at memory-like latency. So let's say server A wants to send a message to server D. What we can do is we can allocate a shared memory buffer from the CXL pool, and then server A can directly write a message to the shared memory buffer. And then server D can read from this buffer to get a message. Given that the CXL latency is about 200 to 300 nanoseconds, communication over CXL in one way is about 0.6 microsecond, which is much faster than the typical RDMA latency in data center, which is about 25 microseconds. So this is especially useful for distributed systems that use consensus protocol, collective communication, or for scale-out databases. So memory pooling and low latency communication are the two key use cases of CXL. So In order to satisfy these two use cases, when designing CXL pod, we need to consider the following requirements. So for effective memory pooling, what we need is to have a large CXL pod so that we can multiplex memory demand across many servers, usually a few dozens. In addition, we want the CXL latency to be low so that we can pool memory for more workload. Having lower latency means that more workload can tolerate the latency of CXL, which means more memory we can pool. I will show more concrete number in the next slide. For communication and memory-like latency, what we need is to have common CXL device between server so that they can use shared memory buffer. However, this is challenging today because of the limited device option. One option is to use CXL switches. So a CXL switch can connect multiple servers as well as multiple CXL devices. However, using CXL switches comes with several drawbacks. First, it incurs higher memory latency, which is about 500 to 600 nanoseconds. This is because CXL switch incur 2 extra serialization and deserialization at every single round trip of memory request. Therefore, our result shows that only 35% of cloud workload can tolerate this level of latency, which result in less poolable memory. Second, it is also expensive to deploy CXL switch because besides purchasing the DIMM and the device, you also have to buy the switches. And each switch can cost up to $5,000, and realistic deployment usually require multiple switches in order to achieve higher bandwidth. On the other hand, the benefit of using CXL switch is that it provides high fan-out. A single switch is able to connect to up to 20 servers. This high fan-out is especially useful for pooling, which require multiplexing among a large set of servers. The other option we have today is to use multi-ported CXL devices, or MPD. So MPD is a type of CXL device where the device itself has a tiny interconnect and exposes multiple ports, where each port can connect to a different server. So MPD today have either 2 or 4 ports available per device. And by avoiding using switches, MPD provides significantly lower latency, about 260 to 300 nanoseconds. Therefore, more workloads can tolerate CXL latency, and our result shows that 65% of the memory can be pooled from CXL. In addition, for MPD, they are cheaper to deploy because you don't need to buy switches. However, a remaining challenge for using MPD is that it has limited fan-out. Each MPD can only connect up to 4 servers. This might hurt pooling because pooling really requires multiplexing among a large set of servers. So we find that the root cause of this problem is because in prior work, we always assumed that the MPD should be fully connected to the same set of servers. So for example, a 4-port MPD connects to 4 different servers. So to increase CXL bandwidth, realistic deployment usually uses multiple CXL devices. And prior work assumed that every single added CXL device, every single MPD connect to the same set of 4 servers. And this is the key factor that limited CXL pod size to be the same as the MPD port count. To solve this problem, we built Octopus. So in Octopus, we break from this prior assumption about fully connectivity and use sparsely connected topology between server and MPD to build larger CXL pod while still using MPD with small port count. So to show what sparsity really means, let's say we have one server S0, and S0 connect to 5 different 4-port MPDs. So unlike prior work where each MPD connect to the same set of server, in Octopus, each MPD actually connect to a different set of server with overlapping. So for example, the first MPD, it connect to 4 server, including S0. And the second MPD, while still connecting to S0, connect to 3 more different server. And it's the same for the other MPD that connect to S0. They each connect to a different subset of servers. And besides S0, the other servers are interconnected similarly with more MPDs. Therefore, by sparsely connecting MPD with servers, we are able to build much larger CXL pod without being limited by the MPD port count. So employing sparsity is a really promising way to build larger CXL pods, but there are many sparse topology. So which one should we choose? So the key question here is how to construct a sparse topology that can serve both memory pooling and low latency communication, the two key use cases as well. We find that, again, this is a challenging problem because memory pooling and low latency communication, they actually have conflicting requirements for the topology. Let me show what that means. So for low latency communication, if a pair of servers need to communicate over CXL, essentially what you need is, so let's say you have a pair of servers that need to communicate. So basically what they need is the set of MPD they connect to must overlap on a common MPD so that they can allocate a shared memory buffer from the common MPD. So the probability really required for low latency communication is to ensure pairwise MPD overlap. And there's actually a family of topology that always guarantee pairwise MPD overlap. It's called balanced incomplete block design, or BIBD. However, the MPD overlap actually affects memory pooling differently. So within a CXL pod, we know that the memory demand is usually highly uneven across different servers. So let's say we know there's a small set of hot servers within a CXL pod that have very high memory demand. So let's say this hot server overlap on a common MPD. If that's the case, the common MPD is going to be the bottleneck of memory allocation, and it cannot really multiplex the memory demand across both hot server and cold servers. Therefore, the ideal topology property we need for memory pooling is to actually avoid MPD overlap so that we can spread the excessive memory demand of the hot server into as many distinct MPD as possible. And the optimal family of topology for this property is the expander graph. So given that memory pooling and low latency communication, they have conflicting requirements in terms of MPD overlap, how can we reconcile these two goals? In Octopus, we reconcile the conflicting requirement with a key insight that low latency communication is typically needed only at modest scale, less than 12 servers. So for example, if you think about consensus protocol, databases, in-memory key value store, the number of participating server, or in other terms, the number of replica, is often very limited. Therefore, in Octopus, we partition a CXL pod into multiple islands, where within each island, we always ensure pairwise MPD overlap using the BIBD topology. Therefore, the inter-server communication within an island always has memory-like latency. And each CXL pod will have several of these islands. To ensure the effectiveness of memory pooling, we interconnect this island with expander-like topologies. By using both BIBD and expander topology in a hierarchical way, we ensure both effective memory pooling and low latency communication, delivering the best of both worlds. To give a quick summary of the different topology, fully connected topology has poor memory saving, and they only support low latency communication among 4 servers. For BIBD, it has poor pooling saving, while it's optimal for low latency communication. For expander graph, it's the complement. It has optimal pooling saving, but it has high communication latency. In contrast, in Octopus, Octopus is able to achieve near optimal pooling saving while still ensuring memory-like communication latency within each island. So for the sake of time, I'm going to focus on the evaluation of the Octopus memory pooling savings. You can find the other result in our paper. So we compare the pooling saving of CXL switches and also MPD with fully connected and with Octopus topology. We use Cloud VM traces from Azure to estimate the pooling saving of different topologies. So in terms of the percentage of pullable memory, because of the high latency, with CXL switches, our result shows that only 35% of memory can be pulled with CXL. In contrast, by using low latency MPD, both fully connected and Octopus can pull up to 65% of memory. Next, for the memory saving within the pooled memory, CXL switch reduced the amount of pooled memory to provision by a significant 44% thanks to the high fan-out. For MPD with fully connected topology, it only has 8% saving because of the limited pod size. With Octopus, in contrast, it built a larger CXL pod and is able to achieve a significant 25% saving. So if we combine the amount of pullable memory with the saving within pooled memory, both CXL switch and Octopus can reduce the total amount of memory to provision by 16%. Besides reducing memory capex from pooling, CXL also adds extra capex cost because we need to purchase the CXL device. So the per server device capex is much higher when you use switches, which is about $3,500 per server, while for MPD, it only costs about $1,500 per server. So overall, Octopus is the only CXL pod that reduced the overall server capex by 3%, while other configurations actually increase the server capex because the device costs outweigh the pooling saving. Although 3% capex saving might seem small, it's significant at hyperscaler scale. And remember, this is an analysis we did before the memory spike. Octopus is only the first step in exploring the design of CXL pod topologies. Here, we actually want to call for more research on designing CXL pod. CXL memory expansion has already been deployed in production, and pooling will be the next to come. There are many exciting research challenges in designing CXL pods. For example, can we borrow some idea from data center network topology? Can we design sparse topology also for switches? Can we design CXL pod for different use case, for CXL 3.0 with multi-level switching, or even for smart CXL devices? Thank you.